So I showed an example where we were working on a pretty nasty logarithm, and we actually considered a whole family of logarithms, and the differences between them are what power of n we're using. And what I showed is that even though you can't get all the integrals because you don't know the value of n, you can relate one integral to a different integral. And so I'll show you an example of that by looking at the family of integrals that is defined by this x to the n times e to the x dx. So here, I'm not going to be able to integrate this because I don't know what value of n is. So I'll get different answers depending on the value of n. But what I can do is try to integrate it by saying that u equals x to the n and dv equals e to the x dx. The reason that's helpful is that du is nx to the n minus 1 dx, and v is e to the x. So I can rewrite my original integral like this, x to the n e to the x, that's uv, minus the integral of v times du. And the beauty of that is what I just realized, or what I just showed really, is that the original integral is equal to this. And the way I did that was I just pulled the constant n in front of the integral. And I have here a reduction formula. The original integral, and then the original integral with n minus 1 as my index instead of n being my index. One other thing I can do here is I can plug in my bounds of integration. They were 0 and 1 in the original problem. So now I know that the integral is really 1 to the n e to the 1 minus 0 to the n e to the 0 minus n times that, which simplifies to just be e minus n times the previous integral. And now here's the beauty of doing all that work. Once you get a reduction formula like that, you can answer questions like this. If I look at I0, that's a pretty simple integral. That's x to the 0, e to the x dx. Well, x to the 0 is 1, so you can just leave it out of the problem. And so you really just have e to the x evaluated from 0 to 1. So e to the 1 minus e to the 0 becomes e minus 1. And that's the last time I need to do an integral, because now I have a formula that I can use that relates the next power to the previous power. So I know I1 is equal to e minus 1 times I0. So in other words, I1 is just e minus 1. Without doing actually any calculus on that part, I know that the integral is equal to 1. So I know the area under the curve. And similarly, I can do I2 this way. I don't even have to do any integration by parts because I had a nice reduction formula. So I2 is related to I1. I1 was equal to 1. So I2 is just equal to e minus 2. And you can see how we can keep going as many formulas as I want. And so that's the idea behind a reduction formula, is you take an integral that looks really hard in general because there's a parameter in it, like an n, so you can't directly integrate it. And so what you do is you find a recursive relationship between n and n minus 1, or maybe n and n minus 1 and n minus 2, like a Fibonacci thing, where the nth term depends on the prior two terms, and that's okay too as a reduction formula. And so just watch out for that, and let me know if you need another example or if you have any questions about that. So thanks for watching.